Welcome to the lecture on Introduction to Polymer Science. My name is Dr. Jinish. I am from Department of Chemistry, Ramaya University of Applied Sciences. At the end of this lecture, students will be able to discuss the importance of polymer science, list the historical milestones in polymer science, define terminologies in polymer science, and classify polymers based on different aspects. We will start with importance of polymer science, why you need to get introduced to polymer science. Go back about the ages of mankind, you will see that human civilization marked by several ages and which are all based on the materials which are mostly used. For example, Stone Age, Bronze Age, Iron Age. Now we have polymer materials age. No matter which industry you are working, whether it is electronic industry, automobile industry, aerospace industry, or manufacturing industry, or which discipline is your research area, biology, chemistry, physics. The basic understanding of polymers is actually very much essential for getting success in your regular activities. As per Lord Alexander Todd, he said, I'm inclined to think that the development of polymerization is perhaps the biggest thing that chemistry has done, where it has the biggest effect on everyday life. He is a Nobel laureate in chemistry in 1957. And now polymers are the new materials of choice. Polymers are one of the biggest achievements in the field of material science in the last century. Polymers are replacing conventional materials such as plastic, metals, wood, and ceramics. Polymers are now new materials of choice in industry. Different types of polymers we are generally using everyday, day-to-day basis. Rubbers, paints, coatings, resins, adhesives, fibers, and plastics. All are polymer derived or polymer materials. If you see the applications of polymers, adhesives, carpeting, cosmetics, fertilizers, for making cables, for making packages, for making pipes, for food packaging, for construction works, for making, medical purposes, everywhere we can see polymers are widely used. Reason behind the acceptance of polymers over other materials, why polymers are being accepted and which are getting more importance than the other materials. One, high strength and load bearing capacity, resiliency, that is comfort giving property, transparency, and lower cost. Except polymers, other materials cannot satisfy all these characteristics. Characteristics such as lower cost, transparency, resiliency, and high strength and load bearing capacity, only polymers can give, and other materials cannot satisfy all these characteristics. Other important characteristics of polymers, they are highly durable, they do not undergo any kind of corrosion, they are lightweight, design flexibility they have, thermal and electrical insulators. Also, they can be prepared from different feedstocks such as petroleum, natural gas, coal, agricultural products, and waste. So from different feedstocks, we will be able to make polymers. Brief history of polymer science. Human beings are using polymers such as wood for food, animal skin, etc. for many civilizations. In 15th century, Christopher Columbus noticed the natives of South America playing a bouncing game with a ball which is collected from exudate of a tree. That at that time he called it as weeping tree. Presently we know that that is natural rubber tree. Joseph Priestley given the name to that solid gum as rubber because the rubber material which we can collect it from natural rubber can erase pencil mark. So Joseph Priestley gave the name eraser or rubber to the solid gum which obtained from that tree. Christian Schoenbein, a Swiss scientist, accidentally discovered gun cotton. He accidentally spilled nitric acid and sulfuric acid on a cotton fabric, and later he found that he got a new material which is known as gun cotton. Similarly, John Wesley Hyatt, he developed a material resembled to ivory and gave the name celluloid. At that time, people were playing uh, snooker or billiards with the balls made up of ivory. So, and ivory was a precious material. So John Wesley Hyatt, he actually made a polymer based material which can be used to make billiard balls. In 1909, Leo Baekeland, he developed the resin Bakelite from phenol and formaldehyde. So this is the natural rubber latex which can be collected from the natural rubber tree. So this is the celluloid billiard ball developed by John Wesley Hyatt. You can see that this can be replaced. This replaced the ivory made billiard balls. Some milestones in the field of polymer science. Charles Goodyear in 1839, he discovered the concept of vulcanization. He found that when natural rubber is mixed with sulfur and when it is heating to 270 degrees Fahrenheit, he found that the rubber got excellent mechanical properties and abrasion resistance. So he found that natural rubber can be made more strengthened with the help of sulfur. X-ray crystallography invented as a method of analyzing crystal structures. So after 8 years, Mr. M. Polanyi, he discovered the chemical structure of cellulose, which is a natural polymer. This established the fact that the polymer unit cells contain sections of long chain molecules rather than small molecular species. After 2-3 years, in 1920, famous scientist Staudinger, he published a paper titled Uber Polymerization. This publication of this paper heralded a decade of intense research and presented the world the development of modern polymer theory. In 1930, polystyrene is invented, and we know that polystyrene is widely used in industry as well as in construction field. 1938, Wallace Carothers of the company DuPont, he produces a well-known polymer product, nylon, and we know that nylon is a common material widely used for making clothes and rocks. 1941, the polyethylene, the commodity plastics widely used now as packaging in packaging industry. So billions of pounds of both high and low density versions of these materials are produced annually for everything from packaging, film to piping to toys. A milestone in the field of polymer science. In 1970, James Economy, he develops the moldable high temperature polymer in the brand name of Econol. This polymeric material paved the way for the development of liquid crystal polymers 1 year later. Econol's most common applications occur in electronic devices and aircraft engines. In 1971, S.K. Wolek, he was awarded 37 patents in polymer science. He developed Kevlar. Kevlar is a high-strength material that can withstand temperature up to 300 degrees Celsius and is used in applications such as bulletproof vest, fireproof garments for firefighting and auto racing. After 5 years, in 1976, the polymer plastic industry outstripped steel as the nation's most widely used material per unit volume. So now we use more plastic than steel, aluminum, copper combined. So we know that the amount of polymers being synthesized or manufactured in the present world. We'll take a class of polymer, which is synthetic rubber, and their brief history. In 1909, a team headed by Fritz Hoffmann, he was working in Bayer laboratory in Germany. He succeeded in synthesizing the first synthetic rubber, which is isoprene. The first rubber polymer, polybutadiene, synthesized from butadiene in 1910 by the Russian scientist Lebedev. In 1931, the American Wallace Carothers and German scientist Hermann Staudinger, they made they led to one of the first successful synthetic rubber known as neoprene. In 1935, German chemists synthesized a first series of synthetic rubbers known as Buna rubbers. They are a kind of copolymers. Other milestones: nitrated cellulose synthesized in 1846, the thermoset plastic produced from milk casein and formaldehyde in 1897, artificial silk, which is rayon, synthesized in 1889, first thermoplastic by adding plasticizers to nitrocellulose was synthesized in 1862. Flexible film of PVC synthesized in 1926. Bakelite introduced in 1907. First isotactic polymerization of propene started in 1954. First aramid fiber marketed by DuPont in 1966. Carothers reported the synthesis of nylon 66. And polystyrene is commercially started synthesized in 1935. Goodyear patented the vulcanization concept of rubber. Hayat uses camphor with nitrocellulose to produce synthetic ivory to make billiard balls. Cross, Bevan and Bredel patent viscose as new artificial silk in 1894. Cellophane synthesis in 1908. High pressure polymerization of ethylene in 1933. Amino resins and aminoplast 1918. First small scale production of polyethylene in 1939. First hydrogel biomaterial in 1960. Ziegler discovered transition metal catalyst for low pressure olefin polymerization in 1953, which paved the path for the more amount of synthesis or the bulk production of polyolefins. Polymers based on acrylonitrile started in 1940. So these are the few milestones in the field of polymer chemistry. Now we'll start with the macromolecular concept. The macromolecular concept came into wide acceptance and appreciation soon after it was propounded by Staudinger in 1920. He proposed long chain structural formula for polystyrene, natural rubber, etc. Long sequences of simple chemical units linked with each other with covalent bonds came into recognition as the basic structural feature of a polymer molecule. Flory and others clearly established that polymer materials consisted of long chain molecules with well-characterized end groups. Now we will study structural features of polymer. The word polymer literally means many means poly, and units means mer. Polymers formed by repeating unit of simply the repeat unit is constituted of a small group of atoms combined in a specific fashion. The simple molecule from which its polymer is obtained or to which a polymer may be degraded is called monomer. So monomer is the simple unit for the polymer. The number of repeat units in a given polymer molecule is known as its chain length or degree of polymerization. Means how many monomers are attached in a single polymer molecule, that is degree of polymerization, and it will give the chain length of that polymer chain. The molecular weight of the polymer can be calculated as the product of degree of polymerization, means the number of monomers in the polymer chain, multiplied by the molecular weight of the repeating unit, molecular weight of the monomer. So if you know the molecular weight of the repeating unit and the number of repeated unit, then you can multiply those two terms, and that will produce the molecular weight of the polymer. So small molecules, they form bigger molecules, which is polymer. And if two monomers are joining, we will call it as dimer. If the number of monomers are between 2 to 10, then we generally call it as oligomer. And even if the number is slightly higher on the higher side also, we'll call it as oligomer. But if the number of monomers are high, then we will call it as polymer. These are the examples of some natural polymers, monomers. For example, proteins is a polymer, is a biopolymer, natural polymer, which is mainly made from the monomer, which is amino acids. Different types of amino acids are there. Phospholipids, a polymer made from the monomer fatty acids. Polysaccharides, generally from monosaccharides. And monosaccharides, we know that they are carbohydrates. DNA and RNA, they are also biopolymers. They are actually, their monomers are nucleotide, and we know that nucleotide is a combination of nucleobases such as adenine, guanine, thymine, cytosine, as well as the monosaccharides such as ribose for RNA and deoxyribose for DNA, as well as a phosphate group. So a phosphate group, a nucleobase, a monosaccharide combine to form a nucleotide, and n number of nucleotide forms the formation of DNA or RNA. So protein, phospholipids, polysaccharides, DNA or RNA, all are natural polymers, and their monomers are listed here. Some polymers and respective monomers and repeat unit structure. Polyethylene monomer is ethylene, and we know the formula of ethylene and its repeating unit, you can see it here. Polypropylene, widely used commodity plastic, its monomer is propylene, which is a gas derived from petroleum. And its structure is given here, and its repeat unit is also given. Polystyrene, derived from styrene, structure is given for styrene, and repeat unit of polystyrene is also given. Polyvinyl acetate, derived from vinyl acetate. Polyacrylonitrile, derived from the monomer acrylonitrile, and their repeat units are also shown here. Other polymers, polyacrylic acid from acrylic acid, repeat unit is given here. Polymethacrylate, methacrylic acid is the monomer for it. Polymethyl acrylate is the monomer for it. Polymethyl methacrylate, widely known as PMMA, methyl methacrylate is the monomer for it. Its repeat unit is very important. We will study about all these polymers in our coming classes. Polytetrafluoroethylene, or another name is Teflon, which is a polymer of the monomer tetrafluoroethylene. The structure of tetrafluoroethylene is given here. Polyoxomethylene, the monomer is formaldehyde, and its repeat unit is CH2O. So these are few polymers and their respective monomers and their repeat units. Now we will distinguish homopolymer and copolymer. In a polymer, if only one kind of monomer is present, the polymer is called homopolymer. Example, polyethylene, polypropylene, polyvinyl chloride, and polystyrene. When more than one kind of repeat units are present in a polymer, it is called a copolymer. For example, nylon 6,6 and bakelite. I will explain it one more time. So in homopolymer, all the monomers are same. Only one type of monomer will be present in homopolymer. Example, polyethylene, where all monomers are ethylene. In polypropylene, all monomers are propylene. In polyvinyl chloride, all monomers are vinyl chloride. And for polystyrene is styrene. At the same time, in copolymer, you can see that there are more than one type of monomer. Nylon 6 is a copolymer which actually made from two different monomers, which are hexamethylene diamine and adipic acid. Same thing, bakelite is a copolymer. Two types of monomers are present in bakelite, phenol and formaldehyde. Based on the molecular weight, we can classify polymers into low polymers and high polymers. Polymers having molecular weight roughly in the range of 1,000 to 20,000 are called low polymers. Polymers having molecular weights higher than 20,000 are called high polymers. So in low polymers, the number of monomer unit will be less, and the molecular weight also will be less. In high polymers, the number of monomer unit in a single polymer chain will be very high. Definitely, their molecular weight also will be very high. Very important things to notice that in a polymer, all polymer chain will not be having the same length. There will be changes in the in the number of monomers in each chain in the same polymer. Low polymers and high polymers again. Why, when we are making polymers, for example, ethylene is a gas, is a fuel. When we are converting ethylene into polymer, we are getting a solid material which is a strong material which can withstand stress. Why these properties are inducing when a polymerization reaction occurs and when we are getting a polymer. Reason, if you see the polymer structure, polymer is made up of so many polymer molecular chains or polymer chains. All these polymer chains are like entangled. You can see that entangled chains. This entanglement gives advantageous properties or strength of the polymers, the toughness of the polymers because of the polymer chains as they are entangled. If you apply some force, they can basically easily dissipate those forces and give you high strength and toughness and so on. So if you apply force on a polymer, that force will be dissipated because of the entanglement. So definitely by dissipating the force, the polymers can withstand more stress, or we can say that polymers are having high strength and toughness. So basically, the high molecular weight helps in providing superior properties like tensile strength, impact resistance, toughness, melt viscosity, and so on. So the major properties of polymer is due to the molecular weight or the entanglement of the polymer chains. Another important property which determines the characteristics of a polymer is the length to diameter ratio. So length to diameter ratio means consider that a polymer molecule which is in chain form. This characteristic difference in length to diameter ratio between a small molecule and a polymer or a high polymer molecule makes all the differences in their physical properties. Due to their long length, molecules in a given sample of polymer material remain in a state of entanglement, both intermolecular and intramolecular. So we can see that because of the long chain, there is a chance of entanglement, and this entanglement leads to both intermolecular and intramolecular interaction between the chains or inside the chain. High melting or softening temperature, high melt or solution viscosity exhibited by polymer materials arise as a consequence of the big size of their molecules and the entanglement of their molecular chains. So if you melt a polymer, the viscosity of the polymer melt will be high. If you dissolve a polymer in a solvent, still the solution viscosity will be very high. The reason for this high viscosity is due to the high molecular weight of the polymer chain as well as the entanglement of the molecular chain. Molecular architecture based linear chains, if a polymer consisting a single continuous chain of repeat units. Here you can see that it's a polymer chain, polymer molecule, it's a single continuous chains of repeat units which are monomers. In branched chains, we will be able to see that there are side chains of repeat units connecting to the main chain of repeat units. Those kind of structure we call it as branched structure or branched architecture. In cross-linked structure, we will be able to see that different polymer chains are connected through some cross-links or some networks. So in linear chains, a polymer consisting of a single continuous chain of repeat units. Branched chains, a polymer that includes side chains of repeat units connecting onto the main chain of the repeat units. Hyperbranched polymer consists of a constitutional repeating unit including branching groups. Cross-linked polymer, a polymer that includes interconnection between the chains. Network polymer, a cross-linked polymer that includes numerous interconnections between the chains. Now we will classify the polymers, different types of classification of polymers. Based on the there are different bases for the classifications. For example, origin, based on the origin, we can classify polymers into natural, semi-synthetic, synthetic. Based on the response towards heat, we can classify polymers into thermoplastic and thermosetting plastics. Based on the mode of formation, we will be able to classify polymers into addition polymers and condensation polymers. Based on the line structure, we will be able to classify polymers based like linear, branched, and cross-linked that we have seen now. Based on the physical properties and applications, we will be able to classify polymers into rubbers, plastics, and fibers. Based on tacticity, different types of polymers such as isotactic, syntactic, atactic polymers can be existed. Based on the crystallinity, we can classify polymers into non-crystalline, which are amorphous, semi-crystalline, and crystalline. So we can classify polymers based on different bases. We will start with the classification of polymers based on the origin. Origin means from where we are getting the polymers. Based on that, we will be able to classify polymers into three. Natural polymers, they are available in nature. For example, natural rubber, natural silk, cellulose, starch, proteins, etc. All these are natural polymers. They are available in nature. Semi-synthetic polymers means they are chemically modified natural polymers. For example, hydrogenated or halogenated natural rubber or cellulosic, esters and ethers of cellulose such as cellulose nitrate, methyl cellulose, or artificial silk such as rayon, which is actually a modified cotton. Cotton is a natural material. So modified cotton, which is rayon, which is a semi-synthetic polymer. Synthetic polymers means they are man-made polymers prepared synthetically. For example, polyethylene, polystyrene, polyvinyl chloride, polyester, phenol formaldehyde resin, all are synthetic polymers. They are generally made from artificial or synthetic roots. So based on the origin, we will be able to classify polymers into natural polymer, semi-synthetic polymer, and synthetic polymers. So a few photos are given: natural rubber sheet, natural rubber silk, cornstarch, in semi-synthetic polymers, cellulose nitrate and methyl cellulose. In synthetic polymers, PVC pipe and its connection, silicone rubber is an artificial rubber, and polypropylene beads. These are all synthetic polymers. Now we will classify polymers based on their thermal response. For example, thermoplastic polymers. They can be softened or plasticized repeatedly on application of thermal energy without much change in the properties if treated with certain precautions. Example, polyolefins, polystyrene, nylon, linear polyesters, and polyethers, polyvinyl chloride, etc. They normally remain soluble and fusible after many cycles of heating and cooling. So thermoplastic polymers, they can be softened or plasticized repeatedly on application of thermal energy. So we can remold every time the thermoplastic polymers by taking some precautions. So it is easy for us to recycle thermoplastic polymers. At the same time, thermosetting polymers, they can be obtained in soluble or infusible forms in early or intermediate stages of their synthesis, but they get set or cured and become insoluble and infusible when further heated or thermally treated. So once you thermally heated, then they will become insoluble and infusible. The curing or setting process involves chemical reactions leading to further growth and cross-linking of the polymer chain molecules and producing giant molecules. Because during the heating, after the use, if you try to heat a thermosetting polymer, then definitely it will form a cross-link, and after that you will not be able to remold it again. For example, phenolic resins, urea melamine resins, epoxy resins, dye-in rubbers, unsaturated polyesters, etc. So if you want to distinguish thermoplastics and thermosetting plastics, thermoplastics often on heating, long chain linear, they normally formed by addition polymerization reaction, can be reshaped and reused. They are soft, weak, and less brittle. They are soluble in certain organic solvents, and we can reclaim them, or we can do recycling. Thermosetting polymers, they do not soften on heating. They have a 3D structure. They generally formed or prepared using condensation polymerization reaction. They cannot be reshaped or they cannot be remolded. They are very hard and strong. and they are insoluble in most of the organic solvents, and recycling is very, very difficult. Now we will study the classification based on the mode of formation of polymers. Addition polymers. They are formed from olefinic, diolefinic, vinylic, and related monomers. So they generally formed from the monomers which contains carbon-carbon double bonds. They all have carbon-carbon linkages along the main chains of the polymer molecule, and usually no other atom appears in the main chain. So if you take an addition polymer, and you can see that the main backbone is made up of carbon-carbon linkages, and normally there won't be any other atom other than carbon in the main chain. These polymers are formed by simple additions of monomer molecules to each other in quick succession by a chain mechanism. This is known as addition polymerization or chain growth polymerization. The examples of such polymers are polyethylene, polypropylene, polystyrene, polybutadiene, and polyvinyl chloride, etc. We will study about addition polymers in detail in our coming classes. Condensation polymers, second types of polymer. They are formed from intermolecular reactions between bifunctional or polyfunctional monomer molecules having reactive functional groups such as OH, COOH, NH2, NCO groups, etc. So in condensation polymer, generally the monomers should be bifunctional or polyfunctional molecule, where the functional groups can be hydroxyl group, acid group, amine group, etc. The related functional groups react with each other in a stepwise manner, producing condensed structural linkages, usually with the elimination of a simple small byproduct molecule in each step of the reaction. So the related functional group react with each other in a stepwise manner, producing condensed structural linkages, usually with the elimination of a simple small byproduct molecule in each step of the reaction. Therefore, beside carbon-carbon linkages, in the main backbone chain itself, there will be other atoms such as oxygen, nitrogen, sulfur. They may be also present in the backbone chain of condensation polymers. The process of their formation is called condensation polymerization or step growth polymerization. We will be discussing this type of polymerization reaction in later classes, in the coming classes. Examples of condensation polymers are polyamides, polyesters, polyethers, polyurethanes, phenolics, epoxy resins, etc. And they are all examples for condensation. Classification based on line structure. First one, linear polymer. They are schematically be represented by lines of finite length. You can see one polymer molecule chain, several polymer molecule chains. They are arranged linearly. So they are formed from mainly olefinic, vinyl, or related polymerization under suitable conditions or by condensation polymerization of bifunctional monomers. So linear polymers are mainly formed from olefinic, vinyl, or related polymerization under suitable conditions or by condensation polymerization of bifunctional monomers. Linear polymers such as high-density polyethylene, polyvinyl chloride, polystyrene, nylon 6, etc. are soluble and fusible. Now, classification of polymers based on line structures. The second one, branched polymers. They can be schematically represented by lines of finite length with a short or long branch of structures of repeat unit. Here you can see that they are lines, polymer molecules as a chain with a short branch or a long branch of the same repeated units. The branches appears as a consequence of uncontrollable side reactions during polymerization or by descents of polymerization. Branched polymers are usually more readily soluble and fusible than linear polymers of comparable chain length or molecular weight. Classification of polymers based on line structure. The third one, the cross-linked or network polymers. They can be represented by a network structure, planar network, as in graphite. We know that graphite is having a planar network of graphene layers. Similar way, we can tell that the network polymers are having the planar network or as a space network, as like in diamond. Cross-linked polymers are insoluble and infusible, as the molecules in them are very giant molecules, often of unusually high or infinite molecular weight. Depending on the nature and frequency of cross-links, such polymers may show different orders of swelling in solvents. Examples are phenol formaldehyde resins, epoxy resins, vulcanized rubber, etc. So representation of the polymers which are linear, branched, cross-linked, and network polymers. Next classification of polymers is based on the application and physical properties. Rubbers, these polymers are characterized by long-range elasticity. They are also known as elastomers. They are weak, dimensionally unstable, and undergo high elongations even on applications of low stresses. They exhibit tensile strength in the range of 300 to 3000 psi and elongation at break ranging between 300 to 1000%. Examples are natural rubber and synthetic rubbers. Technically, rubber is useful if cross-linked to the desired extent. The cross-linking of rubber is commonly known as vulcanization. The rubbery polymers are characterized by low molar cohesion. If you see their molar cohesion force, it is lesser than 2 kilocalorie per gram mole per 5 angstrom of the polymer chain length. Widely used in industry, we call them as elastomers as well. They generally show tensile strength in the range of 300 to 3000, and they elongate at a very high extent, even up to 300 to 1000% if you are cross-linking that elastomer in a proper way. Plastics, second category. These are usually much stronger than rubbers. Some of them are really hard, rigid, stiff, and dimensionally stable, and some of them are soft and flexible. Plastic exhibits tensile strength ranging between 4000 to 15,000 psi, which is quite higher than that of normal elastomers. And elongation at break, it will be lesser than that of elastomers or rubbers, 20 to 200% or even higher. Examples are polyethylene, polypropylene, polystyrene, polyvinyl chloride, nylon, polyamides, urea formaldehyde resins, phenol formaldehyde resins, polycarbonates, all are coming under the category of plastics. Plastics usually exhibits molar cohesion in the range of 2 to 5 kilocalorie per gram mole per 5 angstrom chain length. So it is higher compared to higher compared to rubbers. Fibers, they are the strongest of the three different types of polymers mentioned here. So among rubbers, plastics, and fibers are the strongest. The suitability of fibers, whether it is natural fiber or synthetic fibers, we can use them as textile materials because they have high mechanical strength. It's a tensile strength in the range of 20,000 to 150,000 psi. And also they provide thermal insulation, provide softness and flexibility. Examples of fibers are cotton, cellulose, wool, silk, synthetic polyamides, polyester fibers, acrylic fibers, all are coming under the category of fibers. They usually exhibit molar cohesion in the range of 4 to 10 kilocalorie per gram mole per 5 angstrom chain length. So if you consider the molar cohesion, fibers having higher molar cohesion compared to rubbers and plastics. Next is classification based on tacticity. Tacticity means orientation of monomeric units in polymer takes place in orderly, disorderly with respect to chain, in chain. This orientation affects the physical properties of the polymer. We can classify polymers based on their tacticity as like isotactic, syndeotactic, and atactic. In isotactic polymer, the side groups of the monomers lie on the same side of the chain. If you see, if this is the main chain of the polymer, then the side groups are on the same side of the chain. So we will call them as isotactic polymer. In symbiotic, we can see that there is a regular arrangement, but they are in alternate position. If you see here, the first side group in this side, this alternate is coming here, here, here. So in alternative position, it is arranging, but still it is a regular arrangement. We call them as symbiotic polymers. In atactic polymer, the side groups are arranged randomly, irregularly. These kind of polymers are known as atactic polymer. So based on the orientation of the side group, we can classify polymers into isotactic, symbiotic, and atactic. So here you see for isotactic polypropylene, the bigger group, that is a methyl group, are on the same side of the polymer chain. In symbiotic, we can see that they are in alternate position. In atactic, they are in irregularly arranged. So isotactic, symbiotic polypropylene, atactic polypropylene. For polystyrene, if you see all the side group is a phenyl group, which is on one side, we call it as isotactic, alternate arrangement, symbiotic, and irregular arrangement, we will call that as atactic polystyrene. Next classification of polymers is based on crystallinity. After melting a polymer, if you are allowing it to cool, what will happen? When cooled from molten state, different polymers exhibit different tendencies to crystallize at different rates depending upon the factors such as physical conditions, chemical nature of the polymers, their molecular symmetry, and structural regularity or irregularity. If bulky pendant groups or short chain branches of different lengths are present in the structure of the polymer, then those things will hinder the molecular packing and inhibit crystallization. So based on the crystallinity, we will be able to classify polymers into three: crystalline polymers, polymers showing a high extent of crystallinity, means if the crystallinity is above 60%, normally we will call them as crystalline polymers. Examples: isotactic polypropylene, because of the regular arrangement of the isotactic polypropylene, it shows crystallinity of above 60%. Another one is high density polyethylene, which is linear, regular arrangement is possible, that's why HDPE, high density polyethylene, is also a crystalline polymer. Semi-crystalline polymer, polymers showing a significant but relatively poor degree of crystallinity are termed as semi-crystalline polymers. So in semi-crystalline polymers, a certain area will have crystallinity and the remaining area will be irregular in the arrangement. Those kind of polymers are known as semi-crystalline polymers. For example, low density polyethylene. Amorphous polymers is the third category. These are polymers which are by and large amorphous and have very poor tendency to get transformed onto ordered or oriented structures on cooling to near or even below room temperature. So the tendency to become ordered or oriented structure will be minimum in amorphous polymer. Examples: polystyrene, PMMA, natural rubber, polycarbonate. All are amorphous polymers where the crystalline portion in their structure will be less. So these are the representation of amorphous and semi-crystalline and crystalline areas. Here are a few examples of polymers and their degree of crystallinity and the density in the crystalline region and the density in the amorphous area in their structure are listed here. For nylon, degree of crystallinity is around 35 to 45 and its density in crystalline region will be 1.24 and amorphous it will be 1.08. For polyoxymethylene, degree of crystallinity 70 to 80%, so it is crystalline polymer. Polyethylene terephthalate 30 to 40, so it will be semi-crystalline. Polybutylene terephthalate 40 to 50, so that is also semi-crystalline. Polytetrafluoroethylene, this is Teflon 60 to 80, which comes under the crystalline polymer category. Isotactic polypropylene 70 to 80, crystalline polymer. Atactic polypropylene, because there is no regular arrangement of the side groups. It doesn't follow any kind of regular arrangement when you cool the molten form of atactic polypropylene. It doesn't have any crystalline region or crystallinity, so it's amorphous polymer. High density polyethylene 70 to 80 crystalline, low density polyethylene 45 to 55, it's showing semi-crystalline nature. And we can see that the density of the crystalline region will be always higher than that of the density of the amorphous region. So how amorphous region, the chain structure or the arrangement of the chain in semi-crystalline, in crystalline, see the arrangement of the chain. If regular arrangement is more crystalline. If there is random arrangement or the chains are not at all properly arranged, then it will be having more amorphous region. Now one type of orientation, that is molecular orientation, that is stress-induced molecular orientation in a polymer chain. That means certain polymers, if you try to extend it by applying stress, then the chains will arrange in a certain way, like this here, shown here. It will arrange in a particular way, and that arrangement leads to the formation of crystallinity. And this kind of crystallinity is known as stress-induced crystallinity. So by applying stress, the molecular chains will be arranged in a particular manner, which induces crystallinity, and that kind of crystallinity is known as stress-induced crystallinity. And natural rubber is an example for a polymer which shows stress-induced crystallization. Last classification based on volume, performance and price. Some of the polymers, for example polyethylene, polypropylene, polystyrene, these polymers are widely used in industry, so the volume of the production will be high, but their properties in terms of mechanical strength and all these things will not be very high. So performance wise they are okay, and the price will be very less due to the high amount of production and high amount of availability. There are other sets of polymers like engineering plastic, for example engineering polymers such as nylon, polyester. These polymers, their volume of production is at medium level production, good performance and average pricing. There are high performance polymers, for example high temperature resistant polymers such as high density PTFE, polytetrafluoroethylene, or a temperature resistant fiber such as Kevlar. There the volume of production is less but high performance, obviously price will be on the higher side. So now we studied different types of classification of polymers, and we totally studied 8 types of classification, how